what we're going to have is a set of data points, x and y pairs, those dots, right? Every dot is an x and a y. Then we say I'm going to limit myself to one set of functions, so I can tick off linear and say I'm looking just for linear functions. Then there's a systematic way we can go and find the best fit line. And this is the error here, or the difference between the data y value, data y, and the predicted y. And notice what else we do. We square it, and then we get the total. Sum over all data. Okay. Why do we square it? Squaring seems like a silly thing to be doing. Yeah.
So that like larger errors are amplified and it's long.
So larger errors are amplified, right? So you take 1 squared, it's 1. You take 10 squared, it's 100. So you get a massive scaling effect that is nonlinear. That's actually kind of a bit of a problem in some cases. So I'm not sure that's a reason. It's something we have to take into account, but I'm not sure it's why we'd pick it. It's if we were talking about errors, I'm just as happy if my straight line goes below this data point but above this data point. Those are both errors and they need to be commensurate. So what I'm more interested in is keeping this thing positive. I just want the errors to not cancel each other out. I want all the errors to be positive and help that dictate the line. But we have those two factors. So we're going to square it to make it positive, because squares are always positive. And we're going to have that effect that things further away are going to get squared and so contribute more to the total error than things that are close to the line in the first place. And that's going to play a role. Questions or comments about that? Those symbols, the calculation, or the idea there? Yeah?
You sometimes want to not take into consideration the ones that are far away because they're just outliers.
Absolutely. So there's an issue here, which is if you have some data point that's way, way, way out of the realm of everything else, the best fit line will not be the best fit line because it's trying to accommodate. It's like having the one grumpy student in the class and everyone has to kowtow to that. That's what a best fit line will do to one data point that doesn't fit with the rest. And actually, we're going to talk about that in the next class and see, can we identify those things that we'd call an outlier, something that doesn't seem to fit with the rest of the data, and what does the best fit line do if we leave it in, and what does it do if we take it out? But you're absolutely right. That's going to be one of the problems with this best fit line if we take it in a naive way. So we just talked about that briefly. So if we're doing a straight line fitting, we're going to be taking every data point, finding its distance to the line, above and below, but then we're going to square all those and add them up. And somehow there's going to be one magic line that is the minimum of those errors. Actually, another good reason for this, I think it's the next page actually. Let's get that. First of all, are there other definitions that would make sense? Besides taking those distances and squaring them and adding them up, is there anything else you could think of that would make a reasonable error choice? Absolute, right, absolute value. We squared to make things positive so that above and below is the same. Well, squaring is only one way to do that. We could take the absolute value of y bar minus yi here. Sorry, y hat. Because that makes it positive, and it's perfectly reasonable. And it also doesn't do this thing of magnifying outliers. Honest to God, the reason we do quadratic fits and use it as best fit so often, it's really least squares fitting, and it's because it is easy. And always, little subtext, always gives a unique answer. Okay. And this all comes from calculus. Because if you think about what we want to do, we want to minimize the error. We want to choose our parameters. We want to choose our lines so we minimize the error. If you're going to minimize a function, what was the first step in your minimization? What do you do first? All together. Oh, that hurt. Think calculus class. I'd like to optimize blah, blah, blah. I'm going to do what and set it equal to 0? All together. Take the derivative, exactly. Take the derivative of absolute value. You can't, right? The absolute value, you have to do a whole bunch of stuff. But if you take the derivative of something squared, you bring the 2 down front, blah, blah, blah. It is easy to optimize and find the best fit line because the calculus is super easy for finding the best fit line. That is the reason we like quadratic fits. It works in terms of giving us an answer every time, and it always gives us one answer. It doesn't make things complicated by having multiple lines. It turns out the absolute value is a little more complicated. There are sometimes data sets where there's a bunch of lines that have the same quality by this. That is a lousy reason to pick something. You have to be aware that this is a choice. It's a design choice. It comes with costs, as we'll see next class, the idea of outliers, some other costs as well. But it's a choice because it's easy to implement. So just keep that in mind as we go through this. For now, we'll take that as a stopping point, and we'll look next class at when best fit really definitely is not the best fit because of that quadratic choice.